Today we will be using a new circle approximation method to estimate the value of part of our equation. Next we will be using a bit of hyperspace calculus to find part of our equation to be the volume of a hyperrectangle in the fourth dimension. Next we will wrap everything up by further expanding our already expanded expansion of 2 plus 2 using the previous methods shown in the video and mentioned here.
I apologize for the lack of a conclusion on the last video. For some reason I never bothered to add one. The video just ended with me reviewing VCRs, which is a little off topic, but don't worry. This video will be a bit more formal than the last one, and I do not intend for it to all be time-lapse. So let's get started with this problem right here. This is an expansion of 2 plus 2 that I found in the last video. However, I did have to fix a couple mistakes that I caught myself when I was reviewing everything, getting ready to film. So there's a couple mistakes. The first one right here, and then the second one is right here, and then the sign of this one right here. So let's take a look at this one first. So this one, I used addition notation, which is a capitalized sigma. However, I was planning on using multiplication. I don't know if you caught that. The problem is right here. If you see that right there, I'm just gonna show you. But yeah, I fixed that for this and this. But also another one was for this integral right here. The function, I got a sign wrong. This was supposed to be a plus sign. So yeah, that's another mistake. And there was a couple of sign things. As you can see, the problem right here, I did a lot of multiplication when I should have been doing more division. I mean, not division, addition. Last video, I was stuck on finding the natural log on this and raising it to Euler's number. I don't know if that's in frame. Oh wait, no, it's right here. So natural log raised to Euler's number right there. And I never really did that, so yeah, so the last 20 minutes of that video was pointless, but it's fine. This time, I'll actually be doing stuff, and I'll be explaining it along the way so you guys can better understand. So yeah, this is the main problem right here. I'm going to try and function on a better expansion right here. And so yeah, I'll see you in the lesson.
Alright, so the first thing we're going to do is we're going to try to approximate the area of this circle with radius square root 2 pi. This radius is quite special because this radius, according to my other takes when I actually computed it, if the area of the circle will be equal to 2. So, I've come up with an approximation method to estimate the area of the circle that I don't think has ever been done before. I don't know, just because it's so inefficient. So let's look right here. So let's draw. So for this, you only have to calculate 1/4 of the circle, which is this right here. So I'm going to draw that right here. Alright, and so what you're going to want to do for this approximation is you're going to want to get a ton of lines that intersect it right here. It's best for the lines to stay equal to each other, however, they're not even. So there we go right there, and we're going to represent the number of those lines as n. And we're going to represent the gap as these lines as delta y. So that means that delta y is equal to the radius of the circle over n, aka the number of lines there are. And in order to find the height of each of these, we're going to represent the number of lines. So you have the 1, 2, 3, this is the third line, 1, 2, 3, 4, there's 4 lines in total. But first we have to prove this. So r over 4, so delta y is equal to square root of 2 over pi over 4. And then if you multiply this by 4, you just get that. And so yes, that's the proof that this is what delta y is equal to. How many? So what should we have n be equal to? Let's have n. Let's just see what we can do. 1, 2, 7. Alright, so 1, 2, 3, 4, 5, 6, 7. There we go. Alright. So n is equal to 7. That means delta y is equal to square root of 2 over pi over 7. Alright. So now, what you're going to want to do here is you're going to want to just stretch out these lines. You're going to want to find the intersect right here. So you're going to be representing this as just delta y is equal to. That comes to the other thing I wanted to explain. How do you find the height of this? So what you're going to want to do is we're going to represent u as the number of lines. So 1, 2, 3, 4, 5, 6. So this is line 6. So y 6 is equal to. So we know it's one of the ones on this. Delta y times 6. And so that is going to be the y coordinate of this right here. Assuming that this is the origin right here, because we're just putting this y coordinate. And so then you can do this, and you can calculate the intercept of this, And you're going to also have to calculate the intercept of this right here. So this will just be 7. So y 7 is equal to delta y times 7. Alright. Then you're going to use this to find a hypotenuse line and draw a line straight down. And then, but usually if you want to do this calculation, you're going to have to start from the top, because then the top is going to be a triangle right here. And given that, you can calculate x naught right here, which is, or delta x naught, delta x is 0. And then you're going to do delta y times x naught to find the area of this rectangle right here, and then you're gonna find the x naught of this using the same method, and then you're gonna subtract, my bad, x1, just for labeling's sake. Then you're gonna subtract x naught from x1 to find this gap right here, and then you're gonna multiply this by delta y, and this by x1 minus x naught, and then you're gonna divide it by 2, multiply it by 1/2, and then you found this little area right here, along with this area, and then you keep repeating that until you break it to the x-intercept. Then you multiply that number by 4. I know that's a lot to take in, however, it's quite simple once it's in practice. So, yeah. And another one of my takes, I calculated the square root of 2 over pi, and I don't want to do that again. So I'm just going to use a calculator. So the square root of that will be 0.798884. Or approximately equal to that rounded. And then if you square that and multiply by pi, you should get something that is close to 2. Alright. So now we know that delta y is going to be equal to 7.97884 over whatever we're going to represent this n is equal to 7. So let's divide that. Delta y is equal to. So we know the intercept right here to be, let's create a little list right here. And now we have to find this intercept right here. So wait a minute. I made a mistake.
And what did you know? We weren't that far away from 2. I'm sure I made a couple mistakes with calculating the intercept of each curve right here. However, it is pretty nifty because if you want me to see an expansion of this, I can actually do it here. Just wrong with my notation. However, that will give you the area of this right here. So, what x n is, they're both constants. So look, so x n plus 1. So let's say what I was doing right here is x 3 minus x 2. That would be this. So that'll find this right here. Wait a second. Oh, I just realized something. So this, not sure. This will just be x n minus 1. Because if you wanted to find the area of this rectangle right here, you're going to multiply it by the length of the x I gave before. As you can see, this is the integral right here. If you want, you can prove it. I'll leave that as an exercise for the viewer. And please correct me if I'm wrong. However, I'm pretty sure that this is correct. I'm going to rewrite it in a nicer way so it's easier for you to see. So yes, that is my approximation method that I found. It'd probably just be easier than just to like find the things like this and just create like, I don't know. You know, you've seen it. It's an original approximation method. This is a new approximation method. It's probably hard to integrate this and get pi r squared. I don't know, but it is equal to that. I don't know, fine, integrate it. Do the complete integral and somehow figure out how it gets to pi r squared. I don't know. But of course, if I'm wrong, you will not get to that integral. So I'm sorry for your sent you on a random boost chase to find out. So this, but instead of going to the radius, you go to 2 pi and you multiply this all by 2. That should give you m. So yes, this goes to the first part, and now on to the second part of the video. Alright guys, we finished this, now on to the next part, and I do apologize for the poor lighting. It is around 4 p.m. as of recording this, so yeah, the light's coming harsh from my window right here, but that's okay. So, let's first get rid of all this, and also, don't worry about that. Could have been easier, I could have done it one pass away 2 seconds, but it doesn't matter. So, now we're on to the next part. This part involves a little bit of hypercalculus. In fact, it literally is just hypercalculus. So hypercalculus is calculus, but in more than 3 dimensions, or calculus, but in regards to the amount of dimensions it is in. I'm not going to come up with an example. In fact, because I already have an example. Alright, so, with this right here. Alright, so, you might already be like, oh, where's the 2? Well, I got rid of the 2. Because that thing that I wrote, this thing right here, there wasn't supposed to be a 2. So I just got rid of it. And this should be equal to 0.8. Assuming I wrote this correctly, but you know what it is. So we're just gonna represent this part right here, just 0.8. So I don't have to write that down a whole time every single time. So what we will be doing is figuring out what the side lengths of a tesseract would be if the area is 0.8. So I came up with a formula to find the volume of an nth dimensional rectangle. Here's it right here. Also, yes, I will be using intervals. I swear I'm not addicted to intervals. It just looks, I'm just saying integrating is kind of fun. But if you actually understand integrating what I'm about to write, might seem like the most pointless thing ever. Don't worry, it's fine. Alright, here's the formula to find a tesseract nth dimensional side. So first, this W right here is equal to width. Length is equal to length. Probably misspelled that, whatever. And then n is represented to the number of dimensions. N is equal to the number of dimensions, and E is equal to edge. And the reason I put n plus 2 is because the formula for a tesseract is just all its edges multiplied together. So, I mean for a hyperrectangle, my bad. So E is equal to the edge length. The reason why it's plus 2 is because there's already 2 lengths right here. Alright, so now that we have that out of the way, we can start to figure this out. So now we can write this formula in regards to a 4th dimensional tesseract. This might take up a little bit of space, so I'll write it right here. So let's first
start off with 50. Alright, there we go. And I'm also representing the fourth edge of the hyperrectangle as t for time. I don't know, everyone says time is the fourth dimension, so I decided to go with it. Alright, let's do some integrating. So this should already look very obvious. So a constant, because these are both constants because they're the length of the edges. So it'll be Lx in range from w to 0, which is equal to Lw. So this right here is equal to length times width, which is the two edges multiplied by each other. So we have length times width times, and this should even be even more silly. So using the same thing, it'll be hx from h to 0, and I forgot to mention, this is just, you just plug in h right here. If this would be a function, you plug in the function, which would be the function right here. Whatever. So this would be h times h, or h squared, which is why you would see I rooted it. So it'll be length times width times height. So this is the third dimension, and then there would be this one. And if you do the exact same thing, it'll just be t squared, and then you root that, then you'll have t. So there. That is essentially it. This is the volume of a hyperrectangle. And obviously, if you were to find the volume of a hypercube, or in the fourth dimension, which is where you're doing the tesseract, it would just be just do length cube. And so we will do that. We will represent, since all of these are exactly the same, we will just do L, 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 L. And boom, we have, so then this is L, wait, I read this before, L times L times L times L, which is equal to L to the fourth power. And therefore, the fourth root of 0.8 should be equal to L to the fourth power. Alright. Yep. So, yes. There you go. I don't know what to do next. I guess find the fourth root of 8. Fourth root of 8, I have it written down right here. My calculator is just 0.945 7 4 1, and I always go to the sixth decimal. Everything comes last. Just 0. Completion is 6. So which is equal to L. Alright. So now, theoretically, if we plug in this number into all of these, all the this, and this, we should get 0.8. So let's do that. As you can see, we got essentially 0.8. So yes, there we go. There's a little hint of hyperspace calculus in this. It was not clickbait. Alright. So yeah. Okay, so after all we've done today, let's just put on a larger expansion for M. So I'm going to leave this, and I'm just going to write down the rest of what I had. Alright, here you go, we've done it. And so let's first work on there we go, there's another expansion of 2 plus 2. I hope you enjoyed the video, and I'm quite surprised for how recently this came out, because I immediately got back to work on it immediately after that last video. So yes, there is a menu card, and I didn't have to cheap out to reviewing random stuff. So yes, thank you for watching if you made it this far. This video is a lot shorter and obviously a lot less math. But yes, thank you for watching. Make sure to subscribe if you like this content, and drop a like, and make sure to suggest some music for me to use, because I don't like making music.